Dear learners, I welcome you to another learning video, and I want you to pay full attention as we go through work examples under what we started constructing in the last video, rotational motion. If you have questions in any part or clarifications, please communicate to me via the comment section, and please you can like the video and recommend to your colleagues within and outside the university. Also, click the subscribe button so that you can receive firsthand the latest on this channel. Let's go to the work for today. We have an example. The first example to be considered, say the angular position of an object is given as 2/3 t raised to the power 4 minus 2 t raised to the power 2 plus 5t plus 1. The angular position. So what we have here is what you called theta. What you have here, everything here is theta. And because the value is given in terms of t, that means your theta is a function of t, and this is referred to the instantaneous angular position or angular displacement. The instantaneous at the time t, theta at the time t. So we have to determine the instantaneous angular velocity, which is omega as a function of t, and the instantaneous angular acceleration, that's alpha as a function of t. Then we now obtain the angular velocity when the time is now 0 seconds, and also the angular acceleration. Likewise, angular acceleration when the time is 0 seconds, and also the angular velocity as well as the angular acceleration when time is 1 second. That is, angular velocity, angular acceleration at any instant t, and also at t is equal to 0 second and 1 second. Recall that in this case we have to do some calculus. That's why I encourage you to go back and study the fundamentals, basics of calculus. It's very important for this course. Let's see the solution. We have the solution. We have the angular position given. Then we have the formula for the angular velocity, instantaneous, which is the first derivative of the angular position, the theta dt. And if you solve that, differentiate the expression for angular position with respect to t, then you have what is the final answer, which is the instantaneous angular velocity. That is 8/3 t cubed minus 4t plus 5. And at t equal to 0 seconds, what will be the instantaneous angular velocity? Is substituting t equal to 0, where you have your t in the expression, you have 5 radian per second. Then substituting at t is equal to 1 second, substituting t is equal to 1 second in the expression, and at 1 second the angular instantaneous velocity, the angular velocity now at 1 second will be 2.67 radian per second. Then for the instantaneous acceleration, also recall that for alpha, we have the omega, the t, and if you differentiate omega, the angular velocity with respect to t, then you have 8t squared minus 4. And at 0 seconds, the angular acceleration, substituting 0 seconds where we have t, is minus 4 radian per second. And at 1 second, then the angular acceleration is 4 radian per second. That means at 0 seconds, the object velocity is decreasing, like a negative value. At 1 second, the object's velocity is increasing. That's why we have a positive value. Another example. An umbrella spins with angular acceleration of 3t squared plus 7t. Angular acceleration, omega. So acceleration, alpha, alpha. That's alpha. Angular acceleration, alpha. Now, if its angular position, that is theta, is 5 radians, and angular velocity, that is omega, is 3 radians per second at t is equal to 0 seconds, then obtain the expression for the instantaneous angular velocity and the expression for the angular position. In this case, we know our angular acceleration, and we know that the formula is the omega dt. We can obtain the omega instantaneous value by integrating the instantaneous angular acceleration. Because what value there in terms of t given there is the instantaneous value we can obtain. And likewise, for the angular position, we can further differentiate the instantaneous angular velocity with respect to t, because angular velocity is the theta rather, dt. You integrate, you have using that expression and obtain your value. So let's see the solution. Solution to example P2. Instantaneous value of the angular acceleration 3t squared plus 7t. And recall that the angular acceleration is the time derivative of the angular velocity. So from there, angular velocity means you integrate. If you integrate, you have 3t squared plus 7t in bracket dt, and the value will be t raised to the power 3 plus 7 over 2t squared plus c. C is a constant undetermined. And how do we get that? We can determine it. We know that at t is equal to 0, the omega is 3 radian per second. So substitute 3 radian per second, so you have your omega, and the 0 where you have your t. That is, we have 3 equals 0 is power 3 plus 7 over 2 times 0 squared plus c. And from there, you can obtain the value of c, which will now be included in the final expression t cubed plus 7 over t squared plus 3. Likewise, for the angular position, we can also recall that the angular velocity is the theta dt. So integrating omega respect to t gives us the instantaneous value of the angular position. So t cubed plus 7 over 2t squared plus 3 dt will give us the expression 1 over 4 t raised to the power 4 plus 7 over 6 t raised to the power 3 plus 3t plus d. And this is a constant which can be obtained substituting value of theta, which is 5 radians, when t is equal to 0. So for where I have t substitute 0, and the value of the position at t is equal to 0 is 5 radians. So theta is 5 radians, put 5 radians where you have your theta, then 0 is to the power 4, 0 is to the power 3, then 0. So here becomes 0, if becomes 0, becomes 0. So that means your d is equal to your theta there, which is 5 radians. Okay, and at t equals 0, so actually the final expression now will be 1 over 4 t raised to the power 4 plus 1 over 6 t raised to the power 3 plus 3t plus 5. That's the instantaneous expression. Very easy to do. Another example. Example D3. A disk is rotated from rest a vertical axis with an angular acceleration of 3 radians per second square. Find A, the angular displacement of the line OP, and B, the angular velocity of the disk after 2 seconds. Now look at the question. A disk is rotated. The body is going through rotational motion and is starting from rest. That is, the initial angular velocity, omega I, is equal to 0 radians per second. Then it moves with an angular acceleration alpha, which is 3 radians per second squared. Find the angular displacement. Theta and the final angular velocity, that is when the disk has rotated for 2 seconds. When the disk has rotated for 2 seconds, we'll see what we have. From this now, you know that we have to use one of the equation of motion. So that's why you will be familiar with those equation of motion for rotational motion. So now know the most suited one, where that is the expression where we have all these parameters, we have only one unknown. To tackle theta, then now go for the final angular velocity. So let's see the solution. That's the disk rotating from rest, and time to rotate is 2 seconds. So solution. Rotating from rest, that is omega sub I is 0 radian, then alpha is 3 radian per second. Then we calculate the angular displacement and B, the final angular velocity. Solution. That expression is what we use, where we have theta equals omega sub I t, that is the initial angular velocity time, plus half alpha t squared. Since omega sub I is 0, you have 0. Your t is 2 seconds, you have that. Then your alpha is 3 radians per second, and your t is 2 seconds. You substitute and you compute, you have theta to be 6 radians. 6 radians. Then for the second one, the expression alpha equals rate of change of velocity with time. That is the angular acceleration is the rate of change of the angular velocity with time. And from there, you can make the final angular velocity subject to formula. So you have omega subscript f equals omega subscript I plus alpha t. Likewise, you substitute omega subscript I is 0, then plus the product of 3 and 2, 3 radians per second times 2 seconds. 3 radians per second squared times 2 seconds. So you have 6 radians per second. You get that? This is 0. The unit of this is radian second squared. The unit of this one is seconds. So from there you have 6 radians per second. And that's straightforward. Very easy. Then you have another example. A fan that is turning at 10 revolutions per minute, RPM, speed up to 25 revolutions per minute in 10 seconds. Revolution per minute means velocity. So 10 revolutions per minute is your initial angular velocity, and 25 revolutions per minute is your final angular velocity. And the change took place within 10 seconds. The question is, how many revolutions does the blade require to attain speed? That is, how many rotations? That is, calculate theta. Then, if the tip of the blade is 10 centimeters from the center, you have a fan. Look at the fan, maybe a ceiling fan or a standing fan. Standing fan or a ceiling fan. The fan is rotating. If the blade, the tip of the blade, one blade, the tip is 30 centimeters from the center. That means for the curved part, for the tip of the blade moving along the tip of the blade moving along the curved part, circular part, that means the radius of that circular part is 30 centimeters. So that 30 centimeters is the radius circular part. R. Now calculate the final tangential velocity. That is, tangential velocity is the velocity if the body were to be moving in a linear form. That is, if let's assume instead of going circular now, the tip of this blade just had to disappear, go straight like this. That velocity at which you travel like that is the tangential velocity. I recall that we said this, the product of the radius of the curvature of the curved circular part and the angular velocity. So we will solve that and we'll see how we work with it. Let's go. One revolution is 360 degrees or 2 pi radian, but we are working with 2 radians, so we stick with 2 pi radian. So if the blade should go one complete cycle, the tip, one tip of the blade moves from their initial position and returns to that position once it has completed 1 revolution. And now, before it was completing 10 of such every 1 minute. 10 of such cycle every 1 minute. Then, in 10 seconds, it now moves to covering 25 of such revolution in 1 minute. So we can obtain our value in terms of radian per second. I will convert that straight away. Solution. The initial angular velocity, 10 radian per second, 10 revolution per minute. converted to radian per second. Revolution, one revolution is 2 pi. So that revolution per minute is what we are converted in that, what you have in the parentheses. This revolution per minute is what you have converted, revolution per minute, is what you have converted in these parentheses. Revolution is 2 pi radian, then 1 minute is 60 seconds. And by the time you compute that, you have 1.047 radian per second. That's converting 10 revolution per minute to radian per second. Then you also do the same for the final angular velocity, 25 rpm, the same thing. And your answer will be 2.618 radian per second. And the time is 10 seconds. Find A, the theta, and B, the tangential, final tangential velocity. So to obtain theta, you use one of the very important equation of motion where you have other parameters known except theta. And we have the value omega subscript f squared equals to omega subscript I squared plus 2 alpha theta, where alpha is not known, but how do we obtain alpha? How do we obtain that? Remember that acceleration is rate of change of velocity with time. So angular acceleration is rate of change of angular velocity with time. And you can obtain that from the value, and you answer for the angular acceleration is 0.1571 radian per second squared. Now that we have the alpha, we can now substitute back into the expression we have first, and that expression omega subscript f squared equals to omega subscript I squared plus 2 alpha theta. Thus, we have the expression, and we substitute alpha, making it to a formula. We have alpha to theta as surrogate formula, which is omega subscript f squared minus omega subscript I squared over 2 alpha. And substituting your values, 2.618 squared radian per second, also everything squared, minus 1.047 squared divided by 2 times alpha, which is 0.1571 radian per second squared. From there, remember we said this is your theta, and this now, this expression radian per second everything squared will be radians squared then seconds squared. Then also the unit here is radian per second. Second square will cancel second square. Then radian will cancel 1 radian. So you have radian left. So that gives you the answer. Theta, which is 1. This is 18.325 radians. Then the final initial velocity. We know the radius of the circular part, which is the length of the tip of the blade from the center, 30 centimeters, from that to meter. And so I get our answer in meter per second, the initial velocity, linear velocity. And we know this is R. And we know the final angular velocity. So very easy, straightforward. BF is equal to R omega F. And your R is 30 centimeters, which is 0.3 meters. So the product of the two gives you 0.7854 meter per second. And that was it. Very straightforward. I want you to look at this example. Try and work on it and give me the answer to A, B, and C in the comment section. I believe you have learned a lot through today's video. Again, give it a like, subscribe, and share with your friends and colleagues. I'll see you in the next video. God bless you.